So we talked about feathers and some of the functions of feathers in the previous two lectures, but this lecture is going to focus on flight. So let's talk a little bit about the physics of flight, but let me qualify this by saying that this is definitely going to be a simplified explanation for the forces that are involved. Really, we're going to basically break it down into two forces that have to overcome two additional forces. So if a bird is going to get airborne, first of all, it has to go up in the air, and that's called lift. And lift has to overcome the force of gravity. Well, the other thing that birds typically want to do is move forward. That's the production of thrust. So to move forward, a bird has to produce thrust, and this has to overcome drag, which is trying to hold the bird back. All right, well, let's really focus right now on creating lift, and we're going to use a simplified explanation of just a bird sticking out its wing, kind of just straight like the wings on an airplane. So there are two basic ways that you can generate lift, two different kind of physical aspects that are going on here. One is that there can be a downward deflection of air that is going off of the back of the wing. And if we follow Newton's third law of motion, for every action there is an opposite and equal reaction. So this downward deflection of air is going to create an opposite force of air pushing up on the wing. Okay, so that's one way that we can get lift, to raise the bird and its wing up. This downward deflection of air creating an opposite and equal reaction pushing the bird up. So that's Newton's third law of motion. But we can also understand what's going on with Bernoullis equation. All right, so this isn't really too complex. There are just two components associated with Bernoullis predictions. And that is, we have static pressure represented by P, and dynamic pressure, which is represented by P times V squared over 2. And that exact ratio isn't important for understanding what's going on here. What's important is to understand that the V is associated with some kind of velocity of wind moving over the air, and that's why it's called dynamic pressure. So there's movement of air. You don't see that with the static pressure here, right? It's just P. It's just a pressure. And whatever environment a bird is in, there has to be equal pressure all around the bird and all around its wings. And part of that could be made up of static pressure, and part of it could be made up of dynamic pressure. But it has to remain constant. It's a zero-sum game, so that means if one goes up, the other one has to go down. And that's going to be important to understand what's going on here. So again, just a really simplified example. We've got static pressure and dynamic pressure both above and below the wing, and they have to be the same in both cases. At least the sum of these has to be the same. So that if you have a relative higher number associated with dynamic pressure, well, then you got to have a lower number of static pressure on that side of the wing. So when a wing is just sticking out there and there's no air movement over it, all we have is static pressure, represented by the big red arrows here, right? Because the V is associated with the movement of air, and if there is no movement of air, and you put a V in this formula for the part associated with dynamic pressure, that's a zero. So the only pressure that can exist is the static pressure. Now in a situation like this, therefore, you have to have static pressure equal on top of the wing, on all sides of the wing. That's not going to go anywhere. You're not going to generate any lift in this situation. Now I want you to remember these big red arrows, because we're going to revisit how static pressure can change when you introduce dynamic pressure. The shape of a wing is such that as wind approaches the front of the wing and goes over the dorsal or top part of the wing and the ventral side of the wing, because it's curved, it moves faster over the top of the wing than it does on the bottom of the wing. And that's important. So the air is moving faster over the top of the wing compared to the bottom of the wing. That means there is greater dynamic pressure on the top of the wing, right? So this V number is going to be greater on top of the wing than it is on the bottom of the wing. So we have greater dynamic pressure on the top of the wing compared to the bottom of the wing. Well, let's look at the consequences of that with regard to static pressure now. If dynamic pressure is greater on the top of the wing, then the static pressure on the top of the wing has to decrease more than it does on the bottom of the wing. So just by having any kind of dynamic pressure, you're going to see a decrease in the static pressure. But the more you have an increase in dynamic pressure, the smaller the static pressure is going to be, the resultant static pressure. So since we've got these big blue lines here on top indicating higher dynamic pressure compared to the smaller blue lines and the smaller dynamic pressure on the ventral surface, we're still reducing static pressure, right? Remember how big those red arrows were when there was just no dynamic pressure? You are reducing static pressure, right? Because the pressure, total pressure has to be constant. So if you're adding some dynamic pressure, the static pressure has to go down. But because there's more dynamic pressure on the top of the wing, you have even reduced static pressure compared to the bottom of the wing. So static pressure is going down all around, but it's going down much more on top of the wing. Therefore, the resulting combination of these factors means that you have a relative greater amount of static pressure pointing up on the wing on the bottom. So this generates lift, this pressure differential. Now, one of the ways to prove this is if you just get a piece of paper, a sheet of paper, typing paper or something like that, copy paper, hold it by the tips and just put it underneath your lips so that you blow on the top of the paper. What you're doing is you're stimulating dynamic pressure. You're just blowing on the top of that kind of wing-like piece of paper. What will happen is that paper will rise, okay? Because you're reducing the static pressure on top of that wing, that piece of paper, and the static pressure underneath is going to push that up. All right, ready for demonstration? Pretty good. You can also adjust the amount of dynamic pressure on top of the wing by increasing the angle of attack. That if it's a relatively flat wing, you don't have much of an angle of attack, you're not going to really generate that much lift. But as you increase the angle of attack to some degree, you're going to generate more lift. But when you do that, you also have the potential to lose laminar flow. Laminar flow is the smooth movement of the wind over the wing. And at a low angle of attack, that's pretty easy to do. You just get a little bit of turbulence here at the very end that you can see. And turbulence is associated with drag. It increases drag. So with an increased angle of attack, you start to increase the amount of lift created, but at the same time, you're starting to create this turbulence. And if you get too much turbulence, then you lose lift entirely and you do what's called stalling. So stalling is a result of trying to get too aggressive with your angle of attack and creating too much turbulence and losing that laminar flow. And this is a big problem for birds that have really broad wings. And so there are a couple of things that they can do to maintain laminar flow across their wings at varying angles of attack. One is to just break up your wing so it's not as broad. So there's not as much surface area that has to be kept going laminar flow before the wind gets off the wing. So the wing tips, by separating them, basically what you're doing is you're making those individual primaries like individual wings, right? So you don't have to worry about too much turbulence and losing lift associated with those wing tips. The other thing you can do is have a large alula. So the alula, remember we looked at that in the lab, is a series of feathers that are kind of on the leading edge of the wing, in between kind of where the primaries and secondaries are, and overlapping more of the primaries. What this does is if you compare these two figures here, if you look at the same angle of attack that's pretty steep, you see in the top figure you're starting to get a lot of turbulence, and so you're going to lose lift and you have the potential to stall. But what the Alula, if you add an Alula into the picture, it helps to deflect the wind going over the dorsal aspect of the wing, such that it helps to maintain much greater laminar flow. So this is going to be really important for birds with broad wings that have more of a challenge of a long distance of trying to keep laminar flow, particularly if they're flying in areas where there's low wind. So it's easier to keep laminar flow if you have a lot of fast wind going over the wing. Slow wind is a problem, and also for slow flight this can be a problem. So Alula can really be a big help in this regard. Some other things that you can do is migrating birds oftentimes travel in flocks that are flying in certain formations. And in some cases they fly right behind each other, and you can see this with cormorants, for example, and they're drafting. So they're basically taking advantage of some of the wind flow of the individuals in front of them and gaining a little bit of lift in that way, maintaining some laminar flow. Oftentimes ducks and geese, you see them flying in a V formation, and what is happening here is the tips of the wing create vortices that can be used by the birds behind them to generate a little bit of lift and reduce turbulence. So that's what's going on there. So what about the tail? I talked about the tail previously when we talked about just the names of these as being the rectrices. And I said, the function of it, it's mainly steering, braking, maybe a little bit of lift. Here's a figure of a starling that has been put into a wind chamber, and particles have been put into the wind so that you can kind of see the turbulence. The top figure is supposed to demonstrate the least amount of turbulence, and then as you go down, they took the tail off of the bird with just leaving kind of the coverts. Then they remove the tail and the coverts entirely in C, and this is supposed to demonstrate to you visually that there is reduced turbulence with a true tail, so that a tail may help to keep lift going. So it may generate some lift, or at least reduce the potential turbulence going over the body. I'll be honest, I don't really see it that much in the pictures, but I'm assuming they got some mathematical ways of quantifying this, and so I trust that the tail does serve that function to some degree. But clearly one of the things that the tail does is help in steering. So as a bird is moving through the area, it acts as a rudder and helps them to steer. And then also it does the exact opposite of generating lift. It actually does help them stall out and land. So here you see that with a bluebird. You see that they're changing the angle of their wings so that they're creating a lot of turbulence and stalling on purpose to land. But then they spread their tails to increase resistance as well to help them land. This is particularly noticeable if you're ever banding with a bird, and sometimes the birds will lose their tail feathers when banding. It's certainly something you want to try to avoid, but it does happen occasionally. And if you watch this bird when you let it go and see it land for the first time in a bush nearby, oftentimes what it'll do is it'll overshoot its mark because it's used to having that braking associated with the tail, and they basically kind of crash land for the first time and bypass the intended target branch. So really what we're kind of demonstrating here is soaring flight, where you're just kind of holding your wings out. And again, this works as long as you have plenty of wind, right? To keep that dynamic pressure, that velocity going over the wing to generate a lot of dynamic pressure. Now there are a couple of circumstances in which this is really effective. So one type of soaring is called upslope soaring, where you take advantage of wind going through canyons and hitting large landmarks like hills, and birds can turn into that wind to get that dynamic pressure to generate lift. They elevate, and then if they want to fly in a different direction, then they can just glide downwind from that, now losing altitude in the process of doing that, but then when they want to get more lift, they just turn back into the wind. The soaring, you're probably more familiar with those associated with thermal currents. This is what turkey vultures and black vultures will do around here. They'll find areas where there's thermal upwelling. So temperature differences in the landscape will create these rising currents, and the birds can find these and they just fly in a circle in these, gaining altitude. And then again, if they decide, oh, I want to go that direction, then they can just glide, losing altitude until they find another thermal to gain altitude again. And these birds are really good at finding these thermals by looking at the landscape. So rock outcrops tend to heat up during the day and create these thermals. By looking at cloud formation, so the big cumulus clouds are often indicators of upwellings of thermal activity, and so the birds have learned to use this as well. There's a final way that birds in different environments can use a directional wind. Oceanic areas are oftentimes very, very windy, and the birds do this oceanic wind current surfing, where again they just turn into the wind to gain altitude, and then they fly whatever direction they want, losing altitude, but then before they crash into the water, they turn quickly into the wind again to gain altitude, and just continue doing this back and forth to get where they want to go. Well, let's move on to talking about flapping flight now. Flapping flight is incredibly complex. It can involve up to 50 muscles that can be asymmetrically controlled, so each wing can bend in a different direction at a different time to turn the bird and maneuver in very fine motions. What I really want you to know about this is the two basic parts of the wing and the primary forces that they're generating that makes flapping flight so successful. If you think about it, the primaries in a downward thrust are kind of digging in forward, and they turn forward. So what we were just talking about, how the dorsal aspect of the wing is where you're generating lift. Well, if you just rotate that front part of the wing forward, then you're turning lift into thrust. And so the primaries, as they move forward, that they're turning that lift into a more forward thrust-like motion. But the secondaries during flapping flight generally stay a little bit more horizontal, and so they're primarily responsible for generating most of the lift. Well, to create this flapping flight, you got to have the big muscles. We've already talked about the pectoralis and the supracoracoideus. They make up about 35% of a bird's mass, and so this is a huge contribution to the weight of the bird, but it's crucial to have these big muscles for flight. The position of these is associated with the sternum, is the attachment site, but it's also very central to the body to help maintain a nice center of gravity. So having a center of gravity central allows birds to be more maneuverable. If their wing muscles were concentrated more on the limbs, they would be much less maneuverable. Again, the larger outermost muscle, the pectoralis muscle, is the most important one for the power stroke, the downstroke, and so it is inserted here into the humerus on the ventral surface. The supracoracoideus is the one responsible for the return stroke, and it is underneath the pectoralis, and it wraps around this triosteal canal to the other side of the humerus to help raise the wing and move it back to a beginning position ready for another downstroke. Here's just another detailed look at this. With the pectoralis removed, you can see the supracoracoideus, and we see that the tendon associated with the supracoracoideus is moving into that back proximal part of the humerus going through the triosteal canal. Previously talked a little bit about red or aerobic muscle fibers versus white anaerobic muscle fibers. I'm not going to go over this too much more, but obviously you're going to have more red muscle fibers in species that have sustained flight. So a long distance migratory species like a warbler has primarily red muscle fibers in its wings. A cursorial bird that's running around on the ground, primarily going to have white muscle fibers in its wing, and just the reverse as far as the legs. You know, they're going to run all the time, so they're going to have more red muscle fibers. Something like a warbler is more likely to have more white muscle fibers associated with its legs. Hummingbirds are weird when it comes to flight. Their wing motions approximate more like a figure 8 pattern so that they can generate lift going both forward, what was typically the power stroke, but now the return stroke becomes a power stroke as well. So that means they need power generated by both pectoralis and the supracoracoideus, and indeed these muscles are approximately the same size. And there's a lot greater flexibility associated with the pectoral girdle in a hummingbird too, to make the wings move in this direction. So let's talk a little bit about wing shape and body size in birds and how this influences their flight capabilities. One important thing to consider is wing loading. Wing loading is basically a measure of how big a bird is, weight-wise, relative to the area of its wings. So it's measured in grams per square centimeter. So if you think about a big bird like a loon or a grebe that we saw in the lab, or some of the diving ducks, they're big, they're very heavy birds, and their relative size of their wings has a hard time keeping up. And so they're kind of underpowered wing-wise. And so to get airborne, again, when there's low wind conditions, they have to run across the water to generate enough dynamic pressure to get lift. And they also have to beat their wings more quickly to, again, get that faster airflow, that greater dynamic pressure to keep lift going. Small birds, like most passerines, they're relatively small anyway, and so they have large wings, and so they have what is called low wing loading. So they can just take off pretty easily from just a sitting situation by beating their wings, even if they're in any wind in the area. This bird on the right here, this is a frigate bird. It's a pretty big bird, but it just has these massive wings, and so it's still able to maintain a relatively low wing loading. But that frigate bird had some pretty weird shaped wings, and shapes of wings is also an important contributor to what those wings can do. So something like that frigate bird, or an albatross, or a turkey vulture, they have high aspect ratio wings. So that means that they're relatively long and pretty thin, not very wide. So an aspect ratio is length to width ratio. So albatross, turkey, a vulture, relatively long, skinny wings. Now, when we started getting a turkey vulture, it's still relatively broad too, but they're long enough that they have a relatively high aspect ratio. These are good for gliding, but really bad for maneuvering. You're not going to see turkey vultures soaring through a forest, for example, right? They just don't have that maneuverability. Same thing for an albatross. They just crash into these trees. They just can't turn and make tight movements in closed spaces. Something like a wren or a sparrow, on the other hand, short, stubby little wings, like this here, shown here in B. They, again, they can take off quickly, more maneuverability. They have a combination of low wing loading and a low aspect ratio. So this makes them highly maneuverable in really dense brush, being able to generate lift pretty quickly, but having also very maneuverable wings. But the counter to that is you're not going to see a wren soaring through the air gracefully. They have to beat their wings really hard to be able to fly. So I always kind of contrast this aerodynamically to, if you go to an air show, you see a glider plane, long, skinny wings, right? But if you look at some of these stunt planes, these stunt biplanes, short little stubby wings that give them that maneuverability, but they have these massive engines packed in there. So how are birds as far as efficiency when they're flying? Well, flight takes a lot of energy, but it turns out to get started flying, you need a lot of energy to do that, and that makes sense. You got to beat your wings pretty heavily to get going. But once you get going kind of mid-speed, for most birds, that's when they're most efficient. And then if they want to kind of maximize their rate of flying, it increases their amount of mass-specific power that they use. So this is kind of true for almost all birds. The most efficient speed for them to fly is kind of an intermediate flight speed. Another things that some birds can do to save energy is not just flap their wings constantly. So we've seen some birds like woodpeckers and some of the finches in the field that show flap bounding. So they'll beat their wings to kind of gain an elevation, and then they'll glide. They'll put their wings together, turn into a little torpedo for a short period of time, and then they'll flap their wings again, and they kind of do this kind of sinusoidal up and down jerky type flight. Flap gliding is a little bit the same thing, but it's more kind of long term of each flapping for a long period of time to get elevation and then gliding for a longer period of time, and it's not quite as kind of curvy looking. But the purpose of this, particularly at the medium flight velocities, is to minimize the amount of power used. But this doesn't work for all birds. This is fairly efficient for small birds. But once you get into a larger body size, body mass, it's just not really possible to do flat bounding or flat gliding efficiently. The biggest bird that can do this is our pileated woodpeckers that we see here. And just in general, being a big bird is just not very efficient. So as birds get larger, they're just not capable of generating enough flight. And the reason for that is it's an issue of scaling. So think about, as a bird gets bigger in mass, it's generally increasing at a scale of a cube, right? So length times width times depth. But a wing is basically a two-dimensional structure. So for the mass to be increasing as a cube, it's going to grow much faster than the wings can catch up in 2 dimensions. And so birds, as they get bigger and bigger, they just have to have larger and larger wings that are just a little ridiculous. And eventually you get to the point where you just are too heavy to be able to produce wings that are big enough to generate lift. And some birds don't fly. So some island birds have evolved a loss of flight. So this is a Galapagos cormorant, spends much of its time in the water foraging, and so wings are actually kind of getting in the way in that situation. So they're an energy drain. But also, if you're on an island that doesn't have predators and you don't need your wings to get your food, not only are they potentially costly to keep, but they're just not useful, right? And so actually losing wings and putting on the pounds, particularly in island situations where availability of resources can be kind of sporadic, putting on some weight, keeping some fat to make it through some lean times can be really important. And so if you're not needing to fly anyway and not needing to stay lean to keep flight capable, then just go ahead and put on the pounds and become something like this big cormorant here, or the classic example is the dodo that I started this lecture off by looking at. All right, so that was a general introduction to the simple aspects of flight. The next lecture is going to start looking at foraging in birds, because being an endotherm and having to have a lot of energy to do something like flying means that you have to have some pretty special foraging adaptations.